Hi everyone, I'm Max Holliday.
I'm Peter Knapp.
And I'm Andrew Danetti.
And we are part of the 2013 NASA Aeronautics Academy at Glenn Research Center, where we are characterizing and investigating the failure modes of nickel-based superalloys for use in jet turbine disks. This exciting research can help improve thermal capabilities of these alloys, which can directly increase the fuel efficiency of commercial aircraft by lowering the amount of fuel used during operation.
Turbine engines are used in virtually all commercial aircraft. In these engines, air is compressed into the combustion chamber, where fuel is mixed and ignited. A turbine is used to extract energy from this combustion to power the compressor, and the remaining energy is used for thrust. The turbine disk is one of the most critical components in engine design, as it is subjected to a high-velocity stream of hot gas. The maximum temperature that can be withstood by the turbine disk limits the amount of energy that can be extracted from the fuel, and thus impacts the engine's performance. Materials that can withstand higher temperatures under the harsh operating conditions of the engines are sought to improve engine performance.
The advanced powder metallurgy alloy, Me3, was developed in the NASA High-Speed Research Enabling Propulsion Materials Program in cooperation with GE Aviation and Pratt & Whitney Aircraft Engines. This alloy was designed to have extended durability at temperatures up to 700 degrees C in large disks. The higher temperature capability of Me3 significantly improved fuel efficiency in jet turbine engines and is considered a major advancement in disk alloys. The team we are working with at NASA, along with GE and Pratt & Whitney, won a 2004 R&D 100 award for the development of Me3. Similar superalloys are being utilized in compressor and turbine disks in current and emerging aircraft, such as the Boeing 787 and Airbus A380.
A turbine disk is a fracture-critical structural engine component. Failures are typically uncontained and can result in the loss of an engine, considerable airframe damage, or the loss of the entire aircraft. These advanced alloys are susceptible to surface processing defects and have been known to cause failures. The FAA frequently requires enhanced inspections to detect disk cracking, in order to ensure no uncontainable failures occur. The durability of these material systems was assessed during material and engine development. However, issues emerge as these new components spend more time in service. It would be too expensive and time-consuming to produce hundreds of these disks to test, so we use tensile specimens to observe corrosion effects on alloy life and predict failure initiation. The specimens are corroded using different techniques to help simulate similar engine-like conditions and analyzed on the al-Makan 3D imaging microscope to look at corrosion pit depth, width, and overlap. We use these metrics to predict exactly where the specimen will fail. The specimens are then fatigue tested until failure. Then we use a high-scanning electron microscope to observe the fracture surface and determine the points of failure in a process known as fractography. The data collected during fractography can be used to determine which type of pit initiated crack growth and which type led to failure. So far, we are 85% successful in predicting which pit caused failure, but we are improving with every new data set. These facets of failure analysis not only help characterize the Me3 superalloy, but they allow material scientists to evaluate failed disks and determine exactly where the failure occurred and why.
A key goal of this project is to understand how physical and microstructural factors control the physical properties of nickel-based superalloys. Specifically, the machining of disk features can profoundly affect the fatigue life of these alloys by imparting cold work or surface defects. Additionally, changes in the distribution of phases within these alloys can cause order of magnitude reductions in fatigue life. It is possible to quantify the effects of these processes using a technique called Vickers microhardness testing. In Vickers microhardness testing, a square, pyramidal, diamond indenter is pressed into a surface at a given load. The hardness is then determined from the dimensions of the remaining indent. We can use this testing procedure to create a map of surface hardness to determine the effects of machining. This summer, we are examining broached specimens of NASA's low-solvence, high-refractory alloy that have been cycled to the point of failure, and have already seen preliminary evidence of cold work and phase segregation. Following hardness testing, we will etch these samples to expose the microstructure, i.e. grain and phase distribution, in order to correlate changes in hardness with changes in phase.
One method that can be used to resist the growth of fatigue cracks is to create a residual stress in the surface of the disk. A process known as shot cleaning, where small pellets are fired at the material surface, is used to create a compressive stress layer near the surface that results in external tension and suppresses the growth of fatigue cracks. Residual stress can be measured using a technique known as X-ray diffraction. In XRD, the strain of the lattice is measured to determine the stresses present. By removing different amounts of surface material using a process known as electropolishing, The residual stress profile is a function of depth and can be determined. Understanding these stresses will allow us to better understand how to resist crackling. This summer, we are working to characterize the effect of different shock heating conditions on the residual stresses present in these alloys, as well as to characterize the effect of cyclic loading and elevated temperature conditions on the residual stresses throughout the lifetime.
Our projects involve characterizing aspects related to the failure modes of turbine bases. Current and future work involving the superalloys will help create more efficient and safer aircraft engines.
We would like to thank NASA and our mentors for the opportunity to work on such important and exciting programs, and encourage any and all prospective engineers to consider NASA as an amazing outlet for conducting meaningful and fun research. Thank you.